Many techniques have been developed for the measurement of pressure, and vacuum instruments used to measure pressure are called pressure gauges or vacuum gauges. A manometer is an instrument that uses a column of liquid to measure pressure, although the term is currently often used to mean any pressure measuring instrument. A vacuum gauge is used to measure the pressure in a vacuum, which is further divided into two subcategories: high and low vacuum. The applicable pressure ranges of many of the techniques used to measure vacuums have an overlap. Hence, by combining several different types of gauge, it is possible to measure system pressure continuously from 10 millibars down to 10-11 millibars. Absolute gauge in differential pressures, zero reference. Everyday pressure measurements, such as for tire pressure, are usually made relative to ambient air pressure. In other cases, measurements are made relative to a vacuum or to some other specific reference. When distinguishing between these zero references, the following terms are used. Absolute pressure is zero referenced against a perfect vacuum, using an absolute scale, so it is equal to gauge pressure plus atmospheric pressure. Gauge pressure is zero referenced against ambient air pressure, so it is equal to absolute pressure minus atmospheric pressure. Negative signs are usually omitted. To distinguish a negative pressure, the value may be appended with the word vacuum, or the gauge may be labeled a vacuum gauge. Differential pressure is the difference in pressure between 2 points. The zero reference in use is usually implied by context, and these words are added only when clarification is needed. Tire pressure and blood pressure are gauge pressures by convention, while atmospheric pressures, deep vacuum pressures, and altimeter pressures must be absolute. For most working fluids where a fluid exists in a closed system, gauge pressure measurement prevails. Pressure instruments connected to the system will indicate pressures relative to the current atmospheric pressure. The situation changes when extreme vacuum pressures are measured. Absolute pressures are typically used instead. Differential pressures are commonly used in industrial process systems. Differential pressure gauges have two inlet ports, each connected to one of the volumes whose pressure is to be monitored. In effect, such a gauge performs the mathematical operation of subtraction through mechanical means, obviating the need for an operator or control system to watch two separate gauges and determine the difference in readings. Moderate vacuum pressure readings can be ambiguous without the proper context, as they may represent absolute pressure or gauge pressure without a negative sign. Thus, a vacuum of 26 INHG gauge is equivalent to an absolute pressure of 30 INHG minus 26 INHG equals 4 INHG. Atmospheric pressure is typically about 100 kilopascals at sea level, but is variable with altitude and weather. If the absolute pressure of a fluid stays constant, the gauge pressure of the same fluid will vary as atmospheric pressure changes. For example, when a car drives up a mountain, the tire pressure goes up because atmospheric pressure goes down. The absolute pressure in the tire is essentially unchanged. Using atmospheric pressure as reference is usually signified by G for gauge after the pressure unit, e.g., 70 psig, which means that the pressure measured is the total pressure minus atmospheric pressure. There are two types of gauge reference pressure: vented gauge and sealed gauge. A vented gauge pressure transmitter, for example, allows the outside air pressure to be exposed to the negative side of the pressure-sensing diaphragm, via a vented cable or hole on the side of the device, so that it always measures the pressure referred to ambient barometric pressure. Thus, a vented gauge reference pressure sensor should always read zero pressure when the process pressure connection is held open to the air. A sealed gauge reference is very similar, except that atmospheric pressure is sealed on the negative side of the diaphragm. This is usually adopted on high-pressure ranges such as hydraulics, where atmospheric pressure changes will have a negligible effect on the accuracy of the reading, so venting is not necessary. This also allows some manufacturers to provide secondary pressure containment as an extra precaution for pressure equipment safety if the burst pressure of the primary pressure sensing diaphragm is exceeded. There is another way of creating a sealed gauge reference, and this is to seal a high vacuum on the reverse side of the sensing diaphragm. Then the output signal is offset so the pressure sensor reads close to zero when measuring atmospheric pressure. A sealed gauge reference pressure transducer will never read exactly zero because atmospheric pressure is always changing and the reference in this case is fixed at 1 bar. An absolute pressure measurement is one that is referred to absolute vacuum. The best example of an absolute referenced pressure is atmospheric or barometric pressure. To produce an absolute pressure sensor, the manufacturer will seal a high vacuum behind the sensing diaphragm. If the process pressure connection of an absolute pressure transmitter is open to the air, it will read the actual barometric pressure. Units. The SI unit for pressure is the Pascal, equal to 1 Newton per square meter. This special name for the unit was added in 1971. Before that, pressure in SI was expressed in units such as nm-2. When indicated, the zero reference is stated in parenthesis following the unit, for example, 101 kilopascals. The pound per square inch is still in widespread use in the US and Canada, for measuring, for instance, tire pressure. A letter is often appended to the SI unit to indicate the measurement's zero reference, PSIA for absolute, PSIG for gauge, PSID for differential. Although this practice is discouraged by the NIST, because pressure was once commonly measured by its ability to displace a column of liquid in a manometer. Pressures are often expressed as a depth of a particular fluid. Manometric measurement is the subject of pressure head calculations. The most common choices for a manometer's fluid are mercury and water. Water is non-toxic and readily available, while mercury's density allows for a shorter column to measure a given pressure. The abbreviation WC or the words water column are often printed on gauges and measurements that use water for the manometer. Fluid density and local gravity can vary from one reading to be another depending on local factors. So the height of a fluid column does not define pressure precisely. So measurements in millimeters of mercury or inches of mercury can be converted to SI units as long as attention is paid to the local factors of fluid density and gravity. Temperature fluctuations change the value of fluid density, while location can affect gravity. Although no longer preferred, these manometric units are still encountered in many fields. Blood pressure is measured in millimeters of mercury in most of the world, and lung pressures in centimeters of water are still common, as in settings for CPAP machines. Natural gas pipeline pressures are measured in inches of water, expressed as inches WC. Scuba divers often use a manometric rule of thumb. The pressure exerted by 10 meters depth of sea water is approximately equal to 1 atmosphere. In vacuum systems, the units torr, micrometer of mercury, and inch of mercury are most commonly used. Torr and micron usually indicates an absolute pressure, while INHG usually indicates a gauge pressure. Atmospheric pressures are usually stated using kilopascal, or atmospheres, except in American meteorology where the hectopascal and millibar are preferred. In American and Canadian engineering, stress is often measured in kip. Note that stress is not a true pressure since it is not scalar. In the CGS system, the unit of pressure was the bari, equal to 1 dYNCM-2. In the MTS system, the unit of pressure was the pies, equal to 1 thien per square meter. Many other hybrid units are used such as millimeter of mercury per square centimeter or grams force per square centimeter. Using the names kilogram, gram, kilogram force, or gram force as a unit of force is prohibited in SI. The unit of force in SI is the Newton. Static and dynamic pressure. Static pressure is uniform in all directions, so pressure measurements are independent of direction in an immovable fluid. flow, however, applies additional pressure on surfaces perpendicular to the flow direction, while having little impact on surfaces parallel to the flow direction. This directional component of pressure in a moving fluid is called dynamic pressure. An instrument facing the flow direction measures the sum of the static and dynamic pressures. This measurement is called the total pressure or stagnation pressure. Since dynamic pressure is reference to static pressure, it is neither gauge nor absolute, it is a differential pressure. While static gauge pressure is of primary importance to determining net loads on pipe walls, dynamic pressure is used to measure flow rates and airspeed. Dynamic pressure can be measured by taking the differential pressure between instruments parallel and perpendicular to the flow. Pitot-static tubes, for example, perform this measurement on airplanes to determine airspeed. The presence of the measuring instrument inevitably acts to divert flow and create turbulence, so its shape is critical to accuracy and the calibration curves are often non-linear. Applications: altimeter, barometer, map sensor, pitot tube, sphygmomanometer.